Hello, welcome to this session. So, given that we will use op-amp with NMOS input pair and PMOS current source for VCO, we have to analyze the supply noise rejection. Now, we will bring in the capacitors which are there in the op-amp and see how the supply noise depends on the frequency of the supply noise rejection depends on the frequency of the supply noise. So, our amplifier is this, okay, and we know each transistor comes with its own baggage of capacitors and other things. So, here we are going to use it like this. We will check whether our sign for the amplifier or the feedback is correct. So, this is our oscillator, this is VBN, this is our V control, and okay, and this the voltage, there is no external voltage, but I am just calling this node as VDD VCO, and the average current here is I VCO. You have output of the oscillator as out like this. Okay. Here you have VDD and DC voltage and the noise on the supply. Okay, this is small VDD. Now, just to cross check the sign, if I increase V control because of this NMOS action, this particular node I am calling this as VP, the VP voltage will drop, and if VP voltage drops, what happens is, okay, there is another connection here which is this, yeah. So, if VP voltage drops, you push in more current through the PMOS transistor, I call this as MP, and your VDD VCO goes up. If your VDD VCO goes up with this diode connection, this node potential will go down. If this node potential goes down, then because of the PMOS, you will push in the current and VP will go up. So, this is in negative feedback. Now, you have all the capacitors and other things for each transistor. What we are going to do is we are going to simplify the small signal model of this amplifier as shown. So, here I will say the effective model of this amplifier, it behaves like a current source here, which is GMA. GMA is, stands for the GM for the amplifier. This is your V control, this will be our feedback node, and the effective resistance is R of the amplifier, and effective capacitance, normally the capacitance at the gate of this PMOS transistor dominates. So, is the CGS of the PMOS transistor. So, most of the time this capacitor is dominant, but I am adding all that capacitor as effective capacitance CA. Okay. So, this is the model of the amplifier with this VP, and this particular node is the feedback node which is this particular node, which is this one. Okay. So, when you connect through the PMOS transistor, you have voltage control current source with resistor here, which I call as RDSP for the PMOS transistor, okay, and this current source as GMP times, we have to write it specifically, I will just do that, and the effective resistance of the VCO is R VCO, and normally you will see that there is a load capacitor which comes at the supply of the VCO, which is normally the dominant cap. So, I will write this as CO. This node is a small VDD VCO. Okay. We are looking at small signal analysis. So, I will just write a small VDD VCO, and then you have the supply noise which is modeled like this VDD here. Okay. This connects to the VDD VCO here. Okay. So, this is our feedback. This current source is GMP times Vp minus VDD, because this is the source node. So, this is the small signal model of our supply regulated oscillator, and if I just draw a dashed line, the left side is actually amplifier and the right side is your PMOS current source and the respective load from the oscillator. Okay. Now, given this, we have to look for two things. One, when we are going to use the supply regulated oscillator in the PLL loop, then the bandwidth from your V control to VDD VCO, this particular bandwidth should be larger than the PLL. The other transfer function or the which we want to find is how VDD from the supply noise comes at VDD VCO. Okay. So, that is something which we need to find. So, if I just look at this VDD VCO divided by V control, what we will find here is that this is low pass transfer function with two poles dominantly, and one pole is here. One pole is at the output of the op amp, which you can say omega O, which is the dominant pole, omega amplifier, and the other is at the load, which is omega out. So, these two are the dominant poles which we have in general. Okay. So, let us just look at both these transfer functions. So, let us look at the transfer function VDD by V control. To find this transfer function, one easy way is that you go and calculate the loop gain from V control, and the loop gain from V control you can find by looking at this loop gain. Okay. And this loop gain happens to be equal to, this is loop gain for this regulator loop, this is equal to GMP times RO, GMA times RA whole divided by 1 plus SCA RA into 1 plus SCO RO. Okay. Here RO is equal to RDSP in parallel with our VCO. And normally we can also write that omega A is 1 over CA RA and omega out is 1 by CO RO. So, you see a lot of DC gain, it depends on the DC gain of the amplifier and the DC gain of the PMOS stage. So, the transfer function from VDD from V control to VDD VCO is nothing but loop gain divided by 1 plus loop gain. Okay. Which in turn is a low pass transfer function, and we need to make sure that the bandwidth of this low pass transfer function is larger than the PLL bandwidth. So, if you try to find this bandwidth, let us just look at it. So, we have VDD VCO divided by V control, which is loop gain by 1 plus loop gain. So, I can very well write 1 divided by 1 plus loop gain. This is equal to 1 divided by 1 plus S pi omega A times 1 plus S pi omega O whole divided by GMA RA times GMP RO. Okay. So, you can just write it like this: GMA RA GMP RO whole divided by GMA RA GMP RO plus 1 times S into 1 by omega A plus 1 by omega O plus S square by omega A and omega O. Okay. So, this is the denominator. Now, you have two poles in open loop, in closed loop also you are actually having two poles here. Okay. Now, well, you can decide that which of these two poles is going to be dominant. So, here quite often we use this approximation. If you have a quadratic equation ax square plus bx plus c equal to 0, you know that the roots of this equation can be written that these two roots x 1 plus x 2 is equal to minus b by a, and x 1 x 2 is equal to c by a. If I assume that x 1 is much larger than x 2, then I can say x 1 plus x 2 is equal to, if x 1 is much larger than x 2, okay, is equal to x 1, which this is an approximation by the way, is minus b by a. And then substituting this in the product equation, I can write x 2 as minus c by b. Okay. So, among these two poles, if I am going to apply this concept here, right, and I want to find two poles, then I can very well say there are two poles S 1 plus S 2, these two poles, and this is equal to minus 1 by omega a plus omega o whole divided by 1 by omega a omega o, which is minus omega a plus omega o, right. So, the sum of the two poles is given by this, and if S 1 happens to be much larger than S 2, which implies that S 1 plus S 2 is approximately equal to S 1, which is minus omega a plus omega o. So, effectively you will get one pole at omega a plus omega o. Okay. This is just an assumption here, and by using the same logic, I will have S 2 as, the S 2 pole is equal to minus c by b, right, and what is minus c? Minus c is GMA RA times GMP RO, it is plus 1, I will neglect that plus 1, and this whole divided by 1 by omega a plus 1 by omega o. Okay. So, this is our second pole. I can write this approximately as GMA RA GMP RO divided by 1 by omega a plus omega o. So, in closed loop you are going to get two poles like this. Okay. Now, we can make two assumptions here. If, so let us write first assumption, if omega a happens to be much smaller than omega o, which implies omega a plus omega o is effectively omega o, and 1 by omega a plus 1 by omega o is approximately equal to omega a. Okay. So, this is nothing but saying that omega a plus omega o, the larger value is going to dominate, this is omega o, and in this case because it is 1 by omega and omega o, the smaller one is going to dominate. So, given this, our two poles which we are looking at is that one is at minus omega o, which is not dominant by the way, and other pole is S 2, which is which turns out to be minus GMA RA GMP RO times omega a. This is the dominant pole. Okay, in as per our assumptions. So, if you look at it, the transfer function from V control versus omega, this transfer function is VDD VCO divided by V control. This transfer function I am going to plot in dB, right. So, the DC gain is close to 1 by the way, GMA, RA, GMP, RO and all these things, the DC gain is close to 1, actually slightly lesser than 1, that is fine, right. So, this is like a 0 dB line, and then you get first pole and if in your open loop case your omega A was dominant pole, then in closed loop your dominant pole is S2. So, I just write, let us say this is minus P2 and this is minus P1. It is difficult to write this whole value. So, I will just write P2 here. Okay. So, you get this P2 and then after the P2 you will have omega O or P1 and then you have minus 40 dB per decade, and your omega A is much lesser than. Okay. So, when you are using this particular amplifier in feedback, your transfer function from V control to VDD VCO is shown here, okay, and that has effective bandwidth. This is just I can write the simplified expression VDD VCO by V control is nothing but DC gain is 1 effectively, 1 plus S by P1 and 1 plus S by P2, where P2 is the pole which dominates. So, we should keep our P2 larger than our PLL bandwidth. Okay. Our regulator, this is the VCO regulator. So, the regulator bandwidth has to be larger than, this has to be larger than PLL bandwidth. Okay. The things will just your omega A and omega O will just exchange the role if I say that omega O is going to be dominant. So, in another case I can say everything else will remain the same. Okay. So, for the case here, case 2, if I have previously omega A, now if I have omega O much lesser than omega A, then these roles will just change. This is omega O and this one P1 will be close to omega A, okay. And P2 is nothing but your DC gain times, which is GMP RO GMA RA times omega O. Everything else remains the same. In this case also this has to be greater than the PLL bandwidth. Okay. So, this is simple. Now, we just need to ensure that the regulator bandwidth is greater than the PLL loop bandwidth. Now, we have to look at the expression VDD VCO divided by small signal VDD, right. So, again you write KCL and KVL for this small signal circuit, right, and when you are going to do that you will find the transfer function, okay, and that transfer function is going to be RVCO divided by RVCO plus RDSP times 1 plus SCARA whole divided by, the loop gain remains same. So, you have 1 plus GMA RA GMP RO plus S times CARA plus CORO plus S square times CARA times CORO. This is your exact expression. Now, in this expression I can simplify this expression. In both the cases, if you look at it, this P2 pole, whether it is DC gain times omega A or it is DC gain times omega O, this pole has to be greater than your PLL bandwidth, and this I can call this pole in P2 in all the both the cases omega regulator. Okay. Approximately it is either times omega A or times omega O, but this can be called as omega regulated. So, now I will just write this as RVCO plus RDSP times you have 1 plus SCARA, which is by omega A whole divided by 1 plus S by omega regulated, Okay, that is something which you will have, and then 1 plus S by P 1. Now, this P 1 can be omega A or omega O depending on which of these poles are dominating, and then you have, you take the DC gain outside, you are going to have effectively 1 plus GMA RA times GMP RO. Okay. So, now there are, as we have as we look at the transfer function, there are two cases which you will have. So, let us look at both the cases. In I am going to plot this transfer function, supply noise rejection to the control voltage of the VCO or VDD VCO, this with respect to omega. So, let us choose the first case where omega A is much lesser than omega O. So, if omega A is much less than omega O, I will have omega A as one frequency and omega regulated is greater than omega A. And P 1 pole which we have, P 1 is effectively omega O. So, omega O is coming at P 1 which is omega O. This is what the three frequency which you have. So, the first one is, if you look at it, omega A is a 0. So, first you will get the 0 frequency. So, here you are going to see a 0 frequency, and then you are going to see the regulator frequency, and then you are going to see P 1. So, the transfer function will effectively look something like this. The Bode plot will appear like this. A more smooth curve will something look like this. Okay. So, what you see here is that there is a DC value and then there is a lot of gain, okay, and this is something which is not desired, but this is something which you will get it. What is this value? So, if I call all of this term as, let us say, alpha, right, and this is the 1 over ADC. So, what you are having is alpha times DC part of the loop gain. Okay. So, I can write this as loop gain of 0. And then when the things peak, so what happens at the peak? Peak frequency is slightly larger than your regulator frequency, and this is going to peak value of actually alpha itself, which is RVCO divided by RVCO plus RDS. How are you going to find out? Well, if you see that the peaking is happening after omega regulator and before P 1, you can neglect this term, and what you are going to get here is the value as RVCO by RVCO plus RDSP times omega regulator divided by omega A into 1 by whole of your DC gain, and this is what you know is only RVCO by DSP. Okay. So, this is the case when all this analysis is if omega A is much less than omega O. Then you have another case where I am going to say that omega O is the dominant one, omega O is much less than omega A. So, this is omega O, this will be apparently omega A. Okay. So, in this case, if you go back and look at the expression, what do you have here? So, I will just draw it slightly. So, you get a 0 position does not change, 0 is at omega A. So, you get a 0 at omega A, but before that you get regulator bandwidth. So, in closed loop you get omega regulator pole first, okay, 0 and another pole later, right. And what was the P 1 if you look at it, P 1 or P 2, that was yeah, P 1 is will be omega A. So, the transfer function which you are going to see is something like this. So, first you are going to see omega regulator, and then you will have minus 20 dB per decade. So, we have this transfer function which is VDD VCO divided by V control, and if I say omega O is much less than omega A, then our omega regulator is GMP RO GMA RA times omega O, okay, and omega A is much, and your P1 pole effectively. So, from our equation your P1 is approximately omega A itself, that is an approximation, okay. P1 is at omega A. So, you will see some kind of because you see a pole and 0 effectively. So, you will see this kind of expression, right. And what will be the DC value? Well, DC value is going to be the same what we have checked earlier, which is loop gain of 0. Okay. So, now in this particular case the assumption is that your P1 and your 0 location, they are at the same, but quite often you will see, because this is an approximation, you may see that you get transfer functions like, you may see 0 a little earlier and then you may see a pole. Okay. So, you see two cases, in one case your omega output was dominant, in another case your omega A was dominant. Depending on which pole is the dominant, you will see the supply noise rejection. Okay. What we need to make sure is that our PLL bandwidth, right, in this case if you look at it, our PLL bandwidth has to be lesser than our regulator bandwidth. Okay. That is something which we should make sure. PLL bandwidth has to be lesser than the regulator bandwidth. Now, whether that regulator bandwidth is dominated by the pole at the output of the amplifier or pole at the output load. Okay. So, that is something when we design, we need to take care of that. Okay. Thank you.